I'm Rabin Sugumar. I am one of the founders of Akeana. So I'll be talking about the Akeana portfolio here, focusing on some of the highlights of what we provide. It's a lot of material here, so I'll go through it quickly. If you have any questions, I mean, obviously there'll be a question and answer session now, but if you're not able to get it in there, feel free to send me email. I'm at rabin.sugumar@akeana.com. We also have a booth here, and many of us from Akeana are here ready to answer your questions. So let me get started. So the highlights, right? I'll be talking about a lot of the IP that we provide. Akeana is an IP company. Our business model is to sell IP. So I'll be talking about a lot of the IP we provide, but the highlights would be high-performance cores. So at this point, RISC-V does have cores that are feature set and performance competitive with cores that ARM provides. This is a fact that is slowly percolating into the ecosystem, but yeah, so I'll be talking about our high-performance core line. Uniquely among RISC-V vendors, I would say maybe with one exception, we support SMT. SMT is an application accelerator. So one of the things I'll be showing is for specific applications like certain types of databases, there are huge performance gains to be had with SMT. So aside from running batch processing with SMT on, which can get a 30%, 40% boost, SMT is also useful for accelerating specific applications. Third, I'll be talking about our Alpine test chip. So Lou jokes, that and every time he goes to a RISC-V talk, everybody talks about the best and the first. And how can there be 6 first of anything is kind of a joke. But we do believe this will be the first RVA23 server SoC compliant silicon out there. It is an 8-core test chip that I'll be talking about. And then the last 2 bullets is key to what we do at Akeana. I don't know how much time we'll have to discuss it here, but having IP with all these features is one thing, but putting the IP together in a system that delivers performance, as well as tuning real-world applications to get the performance, is where the challenge really lies, and that's something that we focus on a lot at Akeana. So I'll be talking about some of the material we have that helps with those things, but we would like to discuss what we provide there in greater detail in other settings. This chart is a good summary of the approach at Akeana. So when we started Akeana, we wanted to cover the whole range of cores, right? So in any SoC chip, even if it is a higher-end chip, you do need the high-performance cores. But quite often, in big. LITTLE settings especially, you need mid-range cores as well. And most SoCs have many system controllers for various control functions. And it seemed best to have the support across the space so we could cover all our customers' needs. And so the way we do this is to build one database in System Verilog, but make it highly configurable. So a lot of the features, architectural features that you can think of in a core are parameterizable in our design. So by specifying exactly what the configuration is, we can create cores that are small microcontrollers with less than 100,000 gates, as well as really high-end cores with more than 5 million, 10 million instances, all from a single design database. So using this approach, we cover ARM's entire core portfolio. So this shows on the left, we have ARM's Cortex-M line, for those who are familiar with ARM IP. Those are the RV32 cores, microcontroller type cores. So that's our Akeana 100 series. Then in the mid-range, at the lower end, it's in-order cores. At the higher end, it is out-of-order cores, again corresponding to ARM's Cortex-A line. And then at the high end, it's all out-of-order, corresponding to ARM's Neoverse, going into laptops and other higher-end applications. Okay, I'll keep going. This shows a little bit of detail on our higher-end cores. This is the 5000 series. We can quickly walk through the detail here, but there's no surprises. Wide dispatch. We do support threading in all these cores. We can go up to 4 threads. Floating point and vector support. We can go up to 512 bits on the vector side. Caches, L1, L2. Lots of advanced security features to guard against side channel attacks. We do support PMP, lots of flexibility in the size of the physical and virtual addresses. Of course, virtual memory support. We use AXI, the AMBA protocol, for our interconnects. So the reason for adopting AMBA is obvious. It's a widely used standard at this point. So AXI and ACE comes out of the cores. And then we have an L3 controller that brings out CHI. Power management features, full support for RISC-V debug and trace. And then we also have a little bit on what the comparable ARM cores are. Okay. One thing I would say on that slide, right, is you can see that it's a continuum. They are all derived from the same design database, and the difference is really in how they are configured. And we can mix and match the feature set. It's not locked in stone. A little bit of detail on our higher-end core. As you can see, since it's a continuum with the earlier cores, most of the features are available. There are some additional new microarchitectural features we are working on for this highest-end processor, but it's mostly there. It is RVA23 compliant, 10-wide dispatch. Typically 48-bit addressing, though we can go wider as well. We can support up to 4-way SMT here as well. Similar vector support. L1 IND cache, typically 128 kilobytes. Private L2, typically 2 megabytes, though in specific contexts we can pull it back. Performance telemetry, again, it goes back to delivered performance. So we have capabilities to monitor performance of applications from outside the core. So right now, for instance, if you want to profile an application, you enable the overflow interrupts. And so there is some overhead to performance profiling. And so performance profiling is not widely used. One of the features we have in our core is the ability to profile applications from outside with zero cost. So it lets, especially in a data center context, it lets application system managers look at what the performance is continuously and decide how they want to locate applications. Power management, spec-in rate is 4+ gigahertz. Just to give a sense, the highest end Graviton, right, G4, is little below 3, maybe 3+, or just about 3+. So the performance level is pretty high. Obviously, the threading helps in terms of a rate. And we are engaging with early partners on this. Okay, I may need to speed up a little bit. For SMT, we went through this already. So the key is to focus on the chart at the bottom. There are many of the applications, get like 1.2, 1.3. There are a few applications that obviously drop in performance, but most get 1.2, 1.3. But then there are some outliers there, right? So you get applications where you get 2x speed up, more than 3x speed up. And those are where SMT becomes a feature that it's another tool in the toolbox that we can enable to get really high performance on certain applications. The other use case is in AI. Data movement is an increasingly critical bottleneck for AI use cases. And so SMT is a really good solution for data movement, where you can have lots of outstanding requests from each of the threads. As well as in the heterogeneous compute situation, this is really a software coding advantage. When you have these really low-end cores with real-time OSs or bare metal managing multiple accelerators, it really helps to have threading. So you are not doing context switch in your bare metal, and you can rely on a new thread kicking in to take care of any accelerator completion or response. I'll go through this quickly. Because we have threading and it's configurable, we can go to really highly threaded designs as well. And so we can create these CUDA core-like SIMT cores that we can put together to create an NVIDIA-like GPU architecture. Obviously, there are some software incompatibility issues with the traditional RISC-V approach, and we look at this as more experimental, but this may be a good direction for RISC-V going forward as GPUs become more important in the compute space. A quick summary of our product portfolio. It is a rich product portfolio, but the reason we are able to cover all of this is the fact that we do these highly configurable designs. So the CPU cores we already looked at earlier. The top part of the blue is also cores, but essentially 32-bit cores with vector and 32-bit cores designed for data movement, highly multi-threaded. We do have AI acceleration support in our cores. This is for doing things like exponential sigmoid that is needed for activation functions. We have a line of matrix multiply accelerators, again, highly configurable, and support a variety of arithmetic formats. Non-coherent interconnects based on AXI, coherent interconnects based on CHI. We primarily use this to build out subsystems. As I said, many customers these days don't really want to deal with getting IP from one vendor, interconnects from another vendor, put it all together, and try to make it all work. So they just want a full solution from us. So we have the interconnect pieces to allow us to create these full solutions and give it as a subsystem to the customer, so they don't have to deal with the individual pieces. And then the system IP blocks, which are super important, the interrupt controller and the IOMMU, and the CCB, which is used for building out these small clusters. And then on the tool side, we have GCCM, LLVM optimized for our cores. We have System C models that we can give to our customers that they can integrate with their accelerators and their secret sauce and run applications at the full system level to see what the performance is. And then QEMU for RISC-V development, as well as emulation platforms, Palladium or FPGAs. We do customer training for customers who are using our cores, and remote access to FPGAs and other collateral as well. A quick overview of the scalability options we support. On the top is our single coherent cluster. So this can go up to 8 cores. The cores can be heterogeneous. So this allows a customer that wants a small coherent subsystem to put it together as one piece. And for customers who need more than 8 cores, and sometimes even more than 4 cores, depending on what their performance levels are, it helps to go to the coherent mesh, where they use the CHI hub to build out large-scale systems. And here they can go to hundreds of cores. So we put all of these different pieces together in our Alpine test chip. So it's a proof of concept. It's a software development vehicle. There's a lot of demand for higher-end silicon. IP maturity, there are lots of pieces here, and it really is important to put it all together in silicon to make sure that the IP is mature and works as intended. And there is some product interest. There are a few data centers that are trying to bring up RISC-V-based server farms. It's RVA23 compliant, server SoC spec compliant. There are 8 high-performance out-of-order cores, roughly N1, N2 class, somewhere between N1 and N2, I would say. It's an 8-core Qi mesh. We also have an in-order core, AI core with wide vector and 4-way SMT. So this is really added as a proof of concept for customers who are interested in those configurations. We also have a 32-bit system controller, which acts as our boot core. It includes IOMMU and the PCIe write cache for the PCIe interface, and then memory and other I/O. So this should be taping out in the next few months and should be available Q2 next year. Okay. And all of this also comes together to build out AI solutions. So there are self-hosted solutions where the control core, which is our 5000 series or the higher end of our 1000 series, that acts as the host. There is our matrix multiplication accelerator. There's the interconnect fabric to build it all out. There are AI processing elements that sit next to the matrix multiply unit to do activation functions and other support functions. There's a data movement engine to bring in data in a timely fashion or transpose data. And then there is system management. So we have all the pieces to enable a customer to put together, multi-petaflop chips or chiplets, depending on the case, on their requirements. But you can also use all these in different configurations for highly embedded use cases or mid-range embedded use cases. And using our models, right? So we can provide these system C models or C++ models that we can integrate with the customer IP. So the typical use cases, we provide the cores. Customers typically don't want to do the RISC-V cores because it's a little bit of a lift. So we provide the cores, but many customers like to do their own accelerators, which is where the secret sauce is. And then there is memory, which is has a huge impact on what the final performance of the system is. So the typical use case would be we provide a system C model for our cores. The customer puts it together with their accelerator models and the memory models, and then run their applications at scale to figure out what the performance is, and then we can figure out what tuning needs to be done. We have a range of emulation platforms, both FPGA and Palladium. Most of our cores have been running on FPGA for many years now. And we have Ubuntu booted, Linux and other apps are running. We also have PCIe and SD support on the FPGA, so we can run over NFS from the FPGA. And we have a team that focuses on bringing up apps. So they have so far brought more than 250 applications, brought it up on RISC-V, and they are running it on our FPGAs on a 24/7 basis. This is both to make sure that our silicon and our RTL is doing what it's supposed to do, functional stability, as well as to do application performance tuning for RISC-V. It is a fact, and we have seen this through the years, that just because it runs doesn't mean that it performs well. There's a lot of tuning that goes into these applications that has been done for x86 a lot, and has been increasingly being done for ARM as well. And so for RISC-V to play in this space, a lot of time has to be spent tuning these applications for RISC-V and making sure there are no bottlenecks. And that's it. Thank you.